which by total coincidence is the exact same amount of time as a TED Talk, no pressure. So our first speaker today is Fatemeh Rezaei, and she's going to present work with her advisor, Amir Humantar.
Hi. Thank you for the introduction. In this paper, we introduced TagIt, which is a blind fingerprinting system, which is a blind fingerprinting system. Traffic analysis is the process of inferring information, sensitive information from communication pattern instead of looking at the content, patterns such as packets ordering, size, and timings. There are two main applications for traffic analysis. First, it's detecting a stepping stone, in which by adding a tag to the, by changing the flow entering the network and looking for the change or perturbation in the outgoing flow, they try to correlate to flow in different parts of the network. And the second one is breaking, compromising the anonymity system, such as Tor. Traffic analysis has been studied in two main categories. First, it's passive, which means by just observing the flow in different parts of the network, they try to correlate the flow. And the second category is active traffic analysis, in which by perturbing some features of the flow, they try to make it add a tag to the flow and make it more efficient to make the correlation easier and more efficient. Most of the work in active traffic analysis has been done on watermarking, in which just one bit of information will be added to the flow, when just one bit of information will be added to the flow, and I named some recent works. Recently, a new approach named fingerprinting is introduced, in which instead of adding just one bit of information, multiple bits of information will be added to the flow, which can convey information such as origin of the flow or identity of the fingerprinter. All of the work in this paper, we introduced TagIt. All of the work in previous works is non-blind, which means the fingerprinter has to share the information about the original flow with the extractor, which makes the system non-scalable. In this paper, we introduced the first blind flow fingerprinting system, which reduces the overhead of communication and computation, and therefore makes the system scalable. As I said, TagIt is a blind system, and in TagIt, we use some coding, such as repetition, some error-correcting codes, such as Reed-Solomon, and convolutional code to make the system resistant to the noise. Another thing is TagIt is an interval-based system, which means we look at the packets in the flow in the time intervals. Instead of looking at just one packet and adding the tag, we look at all the packets in one interval and and use all of the packets in the interval to add the fingerprint. We divide each interval to time interval to R number of subintervals, which is the redundancy of the repetition code. Instead of having just one subinterval, we have R number of subintervals, and then we divide each subinterval to M number of slots. Now I want to talk how we add the fingerprint to the flow. This is how one interval looks like. Those blue blocks shows packets. This is a T-length interval. Some of the slots have no packet, and some have some packets. Suppose that fingerprinter wants to embed bit 0 or 1 to the interval. First, it has to choose two sets of permutation functions, mapping functions, P1 and P0. It chooses these two sets of permutation functions randomly and shares these permutation functions with the extractor. Then it has using these permutation functions and choosing a random number between 0 and n-1, because n-1 it uses each permutation and this random number to choose a slot to fingerprinting. You see, by choosing random number 2 and by in this example, fingerprinter wants to embed bit 1, and the random number chosen is 2. So the column 2 of this permutation function is chosen by the fingerprinter, so which maps us to these slots. Then fingerprinter has to delay the packets to the next closest interval, to next closest slot. So this is how fingerprinting. This is how fingerprinter does fingerprinting. Okay, so in the extraction part, as I said, the permutation functions are shared between the fingerprinter and the extractor. The only information that the extractor doesn't have is the random number. So the extractor has to guess what was the random number in fingerprinting. So the extractor should try all the possible options for random number and the permutation with P1 or P0. For example, in here, first guess is that random number is 0 and the embedded bit is P1 is 1. So the extractor chooses P1, and using random number 0, these slots are selected. And as you see, there are not many packets in these slots, so the extractor cannot extract anything using this. So he has to try all of the mappings. Eventually, it gets to the correct random number and correct permutation set. Using these random number 2 and P1, he finds out that 4/6 of the packets are in these selected slots. So, okay, so the extractor gets the maximum of the packets found in fingerprinting slots, and if this maximum number is more than a threshold, which we set to half, the extractor extracts a bit, and depending on which permutation function was used in this maximum value, it extracts bit 0 or 1. As you see, here we have just two permutation functions, P1 and P0, so we can just embed two symbols like 0 or 1. But a fingerprinter can extend the system by adding more permutation mapping functions, like for example, having from P0 to P8. The fingerprinter can embed 3 bits of information in each interval instead of just 1. This table summarizes the parameters of our system, which we haven't introduced all of them, but each parameter makes a trade-off between features such as extraction rate, extraction time, or other things. We show some of these trade-offs in the next slide. We do evaluate our system through some simulations by generating synthetic network flows using Poisson distribution, and by measuring delay between our campus and a couple of Planet Lab nodes. And also we implement our system using some libraries such as NFQ and C++, and using MATLAB communication system for coding part, for implementing Reed-Solomon and the other coding. And these are the nodes that we choose. We choose 4 different nodes, which each one has a different standard deviation of delay to try our system in different settings. These 3 figures shows the simulation result on 3 different lengths. As you see, we fix the number of the R, which is the number of the subinterval, and the redundancy of the system to be a fixed number, and then we increase the slot length. As you see, we can reach extraction rate 1 by having large enough slot length. And this table shows the implementation result on 2 different network settings. And you can see that by choosing the right coding and right parameters, we can reach also extraction rate, good extraction rate 1 or close to 1. And this figure shows the false positive for our system. False positive means a fingerprint, an extractor who doesn't have the keys and who doesn't know if this. False positive means extracting the bit from non-fingerprinted flow. So as you see, as we increase the number of the bits in each interval, the false positive grows. So we have a restriction here to embed like infinite number of bits in each interval. And the last thing is the evaluation of invisibility. As you know, one of the most important features of a fingerprint or watermark is to be invisible. We test invisibility of our system through some tests, which I just talk about one of them, case test, which is used to see if adding the fingerprint or watermark changes the distribution of the flow dramatically and makes it visible. As you see, and here we introduce R-move, which shows the fraction of the packets that we have to move to the selected slots. Because as the rate of the flow grows, moving all of the packets will make the system easily detectable. So we see in these figures that by increasing the R move, the extraction rate also improves, but the KS metric worsens. It means invisibility becomes worse as we increase the R move. So we have to make a balance between the performance and the invisibility by choosing the right parameter for R move. And the conclusion, we introduced the first blind fingerprinting system, which is scalable because it's blind, which is resilient to network noise because of the coding. And by choosing the right parameters, we can have good performance and also, at the same time, plausible invisibility. So I would be happy to answer any questions.
We have a lot of time for questions.
Are you sure?
I think so.